Very good morning, everyone. I hope you can hear me. Okay. So thank you again, Ganga, for inviting me to this workshop. And it's really a pleasure to meet all of you and also people from abroad who have come all the way down here. And also the first talk was really impressive and it really makes my life easy. And I was also quite encouraged by her board work because I was also going to do the same. And I thought, am I going to be the only one who will do the board work? But looking at her, I really got encouraged. Yeah. Okay, so I'll really get started. So I'm giving 3 lectures in this workshop. Today, I will be talking about the classical beam theories. My part of talk is about rods, and I start with classical beam theories, for example, the Euler-Bernouli beam theory and Timoshenko beam theory. Then I'll graduate to nonlinear theory of rods, and I'll see how much time I have. I'll also try to cover up different applications of rods. Okay? All right, so let's get going. So I'm going to talk about theory of beams, and it's classical theory of beams. So first of all, what's the motivation for beam theory? So let me draw, a simple beam-like object. Something like a cantilever, and it may be subjected to distributed load. And then terminal force, as well as terminal couple. And that's the way we have seen this when we talk about beam theories. But of course, it's also a 3-dimensional body. So when you look at it from the 3D perspective, how do these forces and movement, how do they arise? So if I just try to draw it's the same thing from 3D perspective, then it could be that over this cross-section, you have a distribution of traction which is statically equivalent to one force and a moment. Likewise, over the length of this beam, it may be subjected to tractions all over, actually, and in whatever way it could be. And when you transfer these tractions to the center line, it's going to generate an equivalent distributed load and also couple. So at least the external loading that we see here, it's a statically equivalent description of more general distribution over the surface of the body or over the cross-section of the beam. So the loads have been dimensionally reduced, sort of, because now they are just functions of the length, or let's say the arc length of the beam, whereas over here it's sitting on the surface, on the lateral surface, or on the cross-sectional surface and cross-section. So that's the reduction of the load, but also the kinematic description, we also want to reduce that. Why? Because if you want to solve this using 3D elasticity, something that we got started with, we didn't really get to the balance equation, but I'll just write it down. So it's the divergence of the stress tensor equal to 0. And of course, there are different variants of this elasticity equation, Eulerian form, Lagrangian form, or linear elasticity. So maybe let us say this is the linear elasticity equation, divergence of the Cauchy stress tensor, which is equal to 0. And if I expand this in indicial notation, then this is going to be del sigma ij over del xj equal to 0. So when you have summation over j, and I can go from 1 to 3. So there are 3 such equations over here. So this is already a PDE in 3 dimensions. Okay, it's a PDE in 3 dimensions. And you guys know that PDEs are very difficult to solve. I mean, paper and pencil, really forget about it, right? You have to really resort to numerics to solve a PDE. It's a PDE in 3 dimensions. And of course, it's also, you have to say what's the boundary condition. For example, on this surface, it could be clamped, and then you have traction boundary condition. But if you can solve it, which is difficult, but if you can solve it, it gives you the full deformation of the body, right? It could have, for example, I'll draw it here. It could have, well, I could draw here itself. It could become something like this. Right? But it gives you the deformed position of every point where is it going, full description of the deformed body. But also, if you really look at the deformed shape, do we really need the full description? Can we get away with some average description so that you don't have to solve for this PDEs? So that's the question in beam theory. Can we do with just some averaged description of full 3D deformation which does not require solving PDEs? That's where the beam theory comes into picture. Now, if you look at this deformed shape, you can think of a center line, for example. And then you have those cross sections here. You have those cross sections here, which have also deformed. It is very likely that the size of the cross section would change, as you can see here. Over here, you have a larger cross section. Here, you have smaller cross section. Here, you have even larger cross section. It's also likely that the plane section does not remain plane when it has deformed in the exact description. But it turns out when you have a beam-like object where it is slender, meaning the length, the dimension in the length direction is much larger compared to dimension in the transverse direction, that is a cross-sectional dimension. So if you call this as L and this as D, the cross-section need not be circular. It can be rectangular, or it can have an arbitrary shape. And in that case, D will denote some representative length of the cross-section, okay? So D is some representative length of cross-section. So we have beams when L by D is greater than or equal to 10, roughly of this order. It could be 8 or 9 also, it could be 20, it could be 100, it could be 1,000. But L by D would not be, let's say, equal to 2 or 1. Then it's not a beam, okay? So it turns out when you have a beam-like structure, where L by D is of this order, then the cross-sectional deformations, they are not so significant compared to the overall deformation along the center line. And so that's where the beam theory comes into picture. So can we come up with an equation which just gives us the position of the center line? Because as we said, the cross-sectional deformations are not significant. How about approximating this with, let's say, a green chalk, maybe pink chalk? Instead of the actual orange shape, how about approximating that with a pink shape, where the center line would sort of match with the actual orange line. And also the orientation, you can see that it is sort of matching. There is an error, of course, with the actual description. But as we said, that error is insignificant, or it becomes more and more insignificant as L by D gets larger and larger. So, that's why the beam theory is successful. The main point is that the cross-sectional deformation gets insignificant as L by D becomes larger than 10, let's say. So in that regime, instead of solving for the full deformed shape of the beam, one can then do away with just the center line and the orientation of the cross section. So all that you have to do is find out your center line, which could be a curve like this, and start placing cross sections about this center line, because you're also finding the orientation of the cross section. So whatever you found out, it could be that it's like this, perpendicular to the center line, or it may not be that, it's some angle. You start placing a cross section, and then you get an envelope. So that's the deformed shape of the beam, approximate deformed shape, which turns out it does a pretty good job compared to the actual shape, the orange line. It turns out when you actually get your equations for just the center line and the cross-section orientation and construct your deformed shape in this way, it matches with the actual deformed shape quite, to a very small error. So in that way, one could say that beam theory is the mechanics of center line and cross-sectional orientation. And because these variables, the center line and cross-sectional orientation, if it's a 2D deformation, the center line, if you have a coordinate system here can be given through a vector, position vector of the center line. You have this as your kinematic variable. Likewise, the orientation, it can be given by how much has it rotated compared to the horizontal line. With respect to the horizontal line, how much has that rotated, theta. So notice that the two variables, the center line and the cross-section orientation, they are now only functions of the length of the beam, which is being given here through this variable s. Okay? You have r of s and theta of s. So instead of your unknown in 3D elasticity being the deformation map, where you have this little x as some function of big X, so instead of the unknown being a function of three variables here, there are three variables here, big X1, big X2, big X3, as you saw in the first class. And that's why when you want to get an equation for obtaining this unknown, you get a PDE in 3 dimensions. Instead of that, here in this reduced description, the variables that you have here are functions of only the arc length of the beam, just one variable. And therefore, the equations that you will get will just be an ODE. So, that's a very nice reduction from PDE to ODE. So I'll put it here as the variables are functions of just arc length the beam equations are just ODEs instead of PDEs, which you can very easily, not easily, but relatively easily solve. Okay? There's another very interesting thing about beam theory. See, when you go from this 3D picture to the 1D picture, where you reduce the load description from the surface to the center line, a statically equivalent load description, it turns out a given force and moment, for example, that you get here can be obtained through infinite choices of traction distribution. There will be infinite choices of traction distribution, which will give you the same force and moment. So, but when we are solving beam theory, we never bother about what was the underlying traction distribution. We just think, okay, what's the resultant force and moment acting at the end? But if that's the case, then you don't really know which problem you're solving, because in 3D, there are infinite choices for traction distribution leading to the same force and moment. So which 3D problem is really being solved using beam theory? So let me put that also as an important question here. Since a given, or let's say a statically equivalent force and moment can be obtained through infinite choices of traction distribution, which 3D problem is being solved by the beam theory then? That's really a puzzle. Whatever we are solving, is it catering to our own problem or it is some other problem that we are solving? But fortunately, there is a very interesting principle of Saint-Venant principle that comes to our rescue, which says it doesn't matter what your traction distribution is. If all those traction distributions lead to equivalent or lead to the same resultant force and moment, or if the traction distributions are statically equivalent, then the 3D solutions will start to match for different traction distribution as you go away from the point where the traction distribution are acting. So the Saint-Venant principle comes to our rescue, which says if several choices of traction distribution are statically equivalent, then 3D solution corresponding to each of them start to match as you go away from the point of application of load, or point of application of traction in this case. So what this says us is that when you're solving this 3D problem from white to orange, the different orange solutions that you'll obtain will all look the same if you go away from the point where the load is acting, which is if you are far from the boundary, the different solutions will all look the same. They will have very slight error in them, which is really good. Yeah. So for example, here you have this traction distribution. You can reduce them all to one single force and moment. So with respect to everything, yes. Yeah, that's what I mean. Right, so what that tells us is that as you go away from the boundary, different solutions will look the same. So that's really a relieving thing for us that, okay, then we really don't have to worry about what actual 3D problem we were solving because all of them will become the same as you go away from the boundary. Of course, near the boundary, it will show some error, but away from the boundary, they will look the same. And it turns out even near the boundary, the error is not so much. Okay, that's why beam theories are so successful. Okay, so with that picture in mind for the motivation of beam theory, yes. No, the Saint-Venant principle also holds for general bodies. If you have a general 3D body, like a spherical body or a body having the shape of the room, and you are applying a load, let's say, at that corner using different traction distribution, then how will the walls deform? It's the same thing. If you're away from the point of application of the load, the walls everywhere else will deform similarly. So Sandman principle holds not just for beam-like bodies, but also for general three-dimensional bodies. I don't think so. Where does this help is in the fact that when you said no, that you can neglect the cross-sectional deformation. When we are trying to represent this actual deformation with just the center line and the cross-section orientation, that's where this thing helps. When L by D is not so large, then the cross-sectional deformations also become severe. And then just the beam description will not give you the full picture of the actual deformation. Yeah. Say again, don't you also? Well, that will come later on when we actually use a given model, let's say Euler-Bernoulli beam model or Timoshenko beam model or something else. That's where more assumptions will come in. Yeah, but this dimensional reduction, why does this work? That's the main idea over here. Yeah. Yeah, it's right. Yeah, then again, the thing is, because you're just talking about the center line, no? Center line is again away from the actual surface, right? So that's how it works. Yes. Yes. It's both. Yeah. And there is a rigorous mathematical theory when mechanicians prove the center line principle. They have not proved it for the general case, but for special cases they have proved it, and then they have to prove in both. When you asked, is it just with respect to displacement or with respect to also stresses? So depending on what you want, if you want also stresses to be within an error, then you have to go more away from the boundary. If you are just happy with the displacement, then you don't have to go so far away from the boundary. Yeah, but that's a very good question. Okay, so now that we have this motivation, let's talk about the simplest beam theory, which is the Euler-Bernoulli beam theory. So in this beam theory, the first assumption is that cross-section normal and center line tangent are aligned. Remember, we said that beam theory is the mechanics of center line and cross-section orientation. Now, in this theory, the assumption is that both are aligned, which means the two variables become the same, one single variable. Once you know center line, you can then know what will be the cross-section orientation. So they're aligned, no? Once you know the normal, so for example, if you have this center line, then at any point, you think of the tangent, and the cross-section over there has to have the same normal. The normal and tangents are aligned, so the cross-section will simply be perpendicular to this tangent. So once you know the center line, you will also figure out the orientation of the cross-section. Okay, so you can very easily put your cross-sections, and then you have this envelope. Okay, so that's an assumption here. There are many more assumptions that will come as you go down the line. Then the first equation that we start with to derive the beam equation, the Euler-Bernoulli beam equation, is the moment curvature relation. So, I think many of you have done strength of materials, or even in physics somewhere you have seen that the moment that generates in a beam, if I denote that by m for the moment, that's equal to EI, the bending modulus or bending stiffness, times the curvature. Okay? So where E is the Young's modulus and I is the second moment of area. So this is how you can relate bending moment with curvature. Now this is a linear relationship between the bending moment and curvature. When your beam is made up of softer material, let's say rubber, and if you put a very large curvature in the beam, then this linear relation did not hold. Okay, but the Euler-Bernoulli beam theory is based on this assumption also. One was this, and the second one is that your moment curvature relationship has to be linear. All right, so you'll see how we put in more and more assumptions. So this means your curvature K is m by EI. Now, what's the curvature of a curve? So whenever you have a curve, and let's say this is your coordinate system xy. Initially, your curve was, let's say, along the x-axis. And any point here is given by big X, comma, 0, if the curve was originally straight. Then any point along the beam is given by big X, comma, 0, which goes to a point small x, comma, y. Okay? Now, this is the actual curve. What is the curvature of this curve? Many of you would know from differential geometry that curvature is d2y over dx2 divided by 1 plus dy by dx whole square, and then whole to the power 3 over 2. So that's the curvature. And notice here the derivative is with respect to small x, not the capital X. Okay? So that's the formula of curvature, which, as you can see, is non-linear in the unknown y. Now, in Euler-Bernoulli theory, we are going to further linearize this relationship between curvature and the unknown y. That another assumption that is kicking in. Now, how do you linearize this? The derivative is also with respect to unknown x, something that you don't know. So maybe I use different color to also box it. So this was the first approximation. Then that's the second approximation. Now we are going to come to the third approximation, and we will say that small x is same as capital X. It essentially boils down to saying that the displacement in the axial direction is negligible. Okay? So that's the third one. Displacement in axial direction is negligible. Now, once you use this approximation, then your curvature formula becomes d2y over dx2, small x becomes big X, divided by 1 plus dy over d big X whole square to the power 3 by 2. This is still nonlinear in y. We want to be more aggressive. We want to make it more approximate. But it turns, you see, there are so many series of approximations, but finally, what you get really works in many cases. The next approximation, to make this formula linear, I think many of you would have guessed, is that why don't I make the denominator constant? So what is said then is that assume that dy by dx, that's close to 0. And dy by dx has the meaning of, physical meaning of the slope of the curve, right? So that's the next approximation. Slope of the curve is assumed to be small enough. What this means is that when your beam is like this, it can maybe become like this, but it can't become like this, okay? That is not allowed here in the conventional Euler-Bernoulli beam theory. Okay, so now, once you put this in this equation, dy by dx is close to 0, and you have a 1 sitting here, so 1 plus dy by dx whole square is approximately equal to 1, right? It's quite accurately equal to 1. And then your curvature then simply becomes d2y over dx2. Okay? So now we have gotten to the Euler-Bernoulli beam theory, which is, let's come here, put your curvature as d2y by dx2. And your equation is EI d2y over dx2 equal to the bending moment. So that's the Euler-Bernoulli beam theory. It's second order in the deflection y. The bending moment m could also be varying along the length of the beam. A very simple picture is, if you have this cantilever subjected to a terminal load P, then what's the bending moment at any point x along the beam? So you cut a section here and look at the beam. The beam would have, of course, deformed actually. It would have gone like this. You have this P here. And when you cut the section here, this section has got a normal in the negative direction. So the shear force and bending moment that you will see here will also be pointing in the negative direction. This is a cross section with normal in the negative direction to your coordinate system, right? The shear force will also have to point down. That's the convention. If you denote shear force by V, then you have V of x here pointing downward. And bending moment here will also be negative. Or you say that it's clockwise here. On a negative cross section, clockwise bending moment, whereas on a positive cross section, you'll have to have anti-clockwise bending moment. Okay, so that's how your bending moment is, m of x. Now, you have this segment, you can do the moment balance. So this is, let's say you do moment balance about this point itself. You have negative m of x plus moment of this load P about this point, which is going to be P times this distance. Now, as you are away, x away from the clamped end, so this is L minus x. In the deformed shape, this is not exactly L minus x, but as I said, axial deflections has to be assumed to be negligible. So this is, you can approximate this as L minus x. Okay, and then you get m of x equal to P times L minus x. And you can see here, one example here where the bending moment is truly a function of x. And that's something you can then plug in here, and your equation simply becomes EI d2y over dx2 equal to P times L minus x. Okay, and then if you want to solve this, it's a second order ordinary differential equation. It will require two boundary conditions. And where do you get them from? It's from the built-in end, where you say that y of 0 is equal to 0. And also look at the cross-section. The whole cross-section is built in. The cross-section cannot rotate. And the rotation of cross-section is given here by the slope. The cross-section normal and slope are the same in this theory, which also implies that dy by dx is equal to 0. Okay, you plug them in, and you'll get your deflection. Yeah. Yes. Like which? Yeah, I mean, in the actual, the later on when we do the rod theory, you will have a differential equation for the moment. And here you don't need that because this length, although it is not the same as L minus x, but in this Euler-Bernoulli beam theory, we are saying that the axial deflection is negligible. So we are making it L minus x. And then it gets completely determined. So for the Euler-Bernoulli beam theory purpose, you don't need any extra equation. This is good enough. I mean, still then you can simply do the usual moment balance. For example, suppose you had a distributed load acting here, right? Let's say uniformly distributed load given by F, let's say F is the load distribution. So you come to this picture, you have this P acting here, that same V of x, M of x, and then again that load distribution. And this load distribution, for the moment purpose, it is statically equivalent to one single load acting at the center of this piece. So when you find out the net moment balance, you'll have negative M of x plus P times L minus x plus the statically equivalent force, which is F into L minus x. You have a constant F acting over this length L minus x. So total force is F into L minus x. And you are doing moment balance about this point. So the arm of the force is L minus x over 2. So you get an extra term here, F into L minus x whole square by 2, which has to be set equal to 0. And then you get your moment. Okay. So simple statics gives you the moment profile in this case. There can be several interesting cases also here. What if your beam is such that when it deforms, you have a collar here, frictionless collar, and then there is a rod here along which this can slide up and down, frictionless collar. So you're applying a, let's say, a load here of magnitude P. So how do you solve this problem? Again, very simple. If you want to use Euler-Bernoulli beam theory, that is your equation EI d2y over dx2 equal to m of x. So the first task is to get your moment profile. So how do you get your moment profile? So let us say you want to get the moment at a section x, at a distance x from the built-in end. To isolate that beam, you have to isolate that beam. And over here, you're going to have P of x and M of x. But at this end, you are going to have your P and also a reaction moment. Because as you see here, it is fixed on this rod. So the whole cross section here is not allowed to rotate. It has to go as a vertical cross section up and down. So the cross section is not allowed to rotate, which means there will be a reaction moment from the rod. So there will be some MR, let's say, R for reaction, an unknown reaction moment here. With that, once you again do the moment balance, you'll find out that M of x is equal to MR plus P times L minus x. Then you plug that in your equation, EI d2y over dx2 equal to MR plus P into L minus x. You again have a second order ODE, but you also have an unknown MR. So for the second order ODE, you need two boundary conditions, and for the unknown MR, you need one more boundary condition. So this requires a total of 3 boundary conditions. And where do you get them from? The built-in end, as earlier, gives you y at 0 is equal to 0, dy by dx at 0 is equal to 0. Can you figure out the third one? Yes, dy by dx at L is also equal to 0, because this is also, it's not allowed to rotate here, no? Yeah, so with these 3 boundary conditions, you'll be able to solve for the deflection. Okay? You can cook up many more complex problems, and you will still be able to solve them. Yeah. Yes, you'll also have a horizontal reaction. But as I said, no, this is Euler-Bernoulli beam theory, where we are saying that the axial deformation is negligible. So therefore, the axial reaction is also negligible. But if you really want to take into account that horizontal reaction, you will have to solve it using, let's say, elastic rod theory, which we'll do later on. Yes. Yeah. So this beam originally was sitting here, and then a coordinate here is big X, 0. Yeah, that's why they are same. Yeah. Yeah, you can say that, yes. Okay, so that's the Euler-Bernoulli beam theory. Let's now move on to Timoshenko beam theory. Okay. I think almost every lecture will have some flavor of beams. So that's why I think this is a good topic for us to learn. So, yeah. Within the realm of Euler-Bernoulli beam theory. Yeah, I think we should be. Right. Of course, I mean, that's the, for the moment curvature relationship. But somewhere you have to also see how to take this kinematics into account. Yes, but it should be possible, of course. Yeah, that would be a nice exercise. Yeah. Okay, so coming to Timoshenko beam theory. So here we are going to relax the first approximation that the cross-section normal and centerline tangent are aligned. So we are going to relax this relaxation, which will mean that you will have two unknowns now in this Timoshenko beam theory, the centerline variable and also the cross-section orientation. So cross-section normal is no more aligned with the centerline tangent. What this means in terms of picture is that so you have this curve, centerline curve, and at any point you have the slope but the cross-section normal will not be aligned with the slope. So the cross-section could be like this. And the cross-section normal is then like this. Okay? So think of a horizontal reference line here with respect to which you are going to measure the angle. So initially the cross-section was vertical, and therefore the angle between the blue line and the horizontal would be 0. But now the cross-section has rotated like this. So that's your angle here, theta. And the yellow angle that you see here, okay, so this is, of course, the blue angle, theta. But then you also have the yellow angle. Can you guess how much is this going to be? So that's the angle that the slope is making. Tan inverse dy by dx, isn't it? Tan inverse dy over dx. Let's say if that's alpha, then alpha is equal to tan inverse dy by dx. So and this angle between the blue line and the cross section, that is 90 degrees. Okay, now see, originally the cross section normal and center line tangent, which is the orange line here, originally the angle between them was 90 degrees, right? In the reference configuration, your beam was like this. The cross sections were perpendicular to the center line. But now, the angle between the white line and the orange line, it's no more 90 degrees. Can you figure out how much is that angle? So the angle between orange and the blue line, that's 90 degrees. Sorry, between white and blue line, that's 90 degrees. So how much is this angle then? Exactly, theta minus alpha. So the angle between the white line and the orange line is then going to be, right, so that's pi over 2 plus theta minus alpha. That's the angle between the white line and the orange line. Angle between white and orange line. And the original angle between the same was pi by 2. So there are two material lines here, the center line tangent and the cross-section line, and the angle between them have changed. So whenever there is a change between angle, it leads to shear, right? So shear is defined as gamma is original angle minus the current angle. The original angle is pi by 2 minus the current angle, which is over there. So your shear is simply alpha minus theta. That's the shear. Okay? And alpha is tan inverse dy by dx minus theta. And that's your gamma. And because dy by dx is very small, we are not relaxing that assumption anymore. Only this assumption was relaxed. Rest all assumption is there. So tan inverse dy by dx is going to become dy by dx. So that's your gamma. We are not done yet. So that's the gamma at the centroid of the cross section. If you really think of the beam now, and here is your cross section, and that's your center line, you found out gamma at this point. If you look at it from the 3D perspective, you found out gamma at this point, center line tangent and the cross-sectional line. It turns out this gamma varies along the cross-section. Do you guys remember from strength of materials? When you have a rectangular cross-section, the shear stress, for example, varies quadratically. If you draw the profile for shear stress, it's 0 at the ends, at top and bottom, and max at the centroid of the cross-section. So we are looking at the shear at the centroid, where it is usually maximum. So I'll say this gamma at centroid C, gamma at C. But the shear strain is also proportional to shear stress, right? So This implies tau shear stress at C over G, which will give you shear strain, right? Shear stress is G times shear strain. Tau over G is equal to dy by dx minus theta. Now, this tau shear stress is 3D thing. It's a 3D stress. But in beam theory, we are working with forces and moment. We are not working with stress. Can we write this in terms of stress? So first of all, what do you think would be the average shear stress in the cross section? If the shear stress here, when you cut it, the total shear force, look at this. Now this is a cross section with positive normal in the positive direction. So shear force will be positive upward. That's V of x. And bending moment here will be anti-clockwise positive, M of x. Now, if the shear force in the cross section is V of x, then what's the average shear stress? Force divided by the area of the cross section, right? So tau average is V by A. But how much would be tau C? What would be the shear stress at the center? Which for example, for rectangular cross section is highest at the center. It is different from the average shear stress. So that's where you have this concept of correction factor. Okay, so this is going to be V by some correction factor, let's say K, but do not confuse this K with the curvature over there. Okay, that curvature is Greek. This is straight K. Okay, K times A. That's your tau C, which you can now plug in here. And then you get dy by dx minus theta is equal to V of x over the correction factor K G A. So this is one of the equations of the Timoshenko beam theory, which has your unknown y and also the unknown theta. You, of course, need one more equation because there are two unknowns, so you need two equations. Yeah. V is the shear force in the cross section. In the cross section. Yes. Right. And in these theories, we are only interested in the vertical component, the shear force component only. The axial force component, we don't talk about that. Yeah. The K is the shear correction factor, and A is the cross-sectional area. A is cross-sectional area. Yeah, that's it's a problem in its own, actually. So this is shear correction factor. So what you really do is you have to solve the actual cross-sectional problem. And in case of rectangular cross-section, there are a strength of material solution, which says that the shear stress tau varies in the cross-section using this strength of materials formula, VQ over IT. There are more symbols coming up. But this is an approximate strength of material solution for the variation of shear stress. Once you know this shear stress variation, you just find it out at the center and divide that by the average shear stress. That will give you correction factor K. For rectangular cross-section, this correction factor is usually, it is 2 by 3. for rectangular cross-section. Yeah. Okay, so I mean, you can forget about how you get it for now. Just assume that there is a correction factor. The shear stress at the center is not the same as the average shear stress. And therefore, you need this correction factor. It depends on the shape of the cross-section. If it's circular, it is something else. If it is rectangular, it is something else. If it is trapezoid, it is something else. Okay? Anyway, so I should maybe write this here. Tau equal to VQ over IT. So that's just one of the equations that we have gotten. We need one more equation. How do we get that equation? That part of the equation that we have, EI d2y over dx2 equal to m of x. But it turns out we can't use this anymore because the actual bending rigidity is not the curvature of the center line. When you actually look at a beam, the center line could do whatever it wants to. But in bending, why does really bending moment arise? Is because if you look at two neighboring cross sections, as they bend, on the top side, it is, for example, pushing each other. On the bottom side, it is pulling each other. So perhaps it's going to become something like this. Only then the top will be pushing each other and the bottom will be pulling each other. So that description is not going to come through the center line unless the center line and the cross-section normal are aligned. Then it's a different thing. But in this theory, because they are not aligned, center line, tangent, and cross-section normal, they're not aligned. So you have to independently look at the cross-section normal. And then you have to see how is the theta varying. If the theta is the same, then there is no tendency to push on one side and pull on the other side. It's only when the theta is varying that you get that tendency, which will lead to variation in the normal stress in the cross-section, and likewise generation of bending moment in the cross-section. So the curvature in this case is not d2y by dx2. The curvature here is d theta by dx. It's coming through the change in orientation of the cross-section. It has got nothing to do with the center line curvature. Okay? So once we see that, then the second equation is, of course, the EI d theta over dx equal to m of x. And what you have to remember is that, because as you see here, dy by dx minus theta is this. So d theta by dx, when you differentiate this, this is, by the way, equation number 1, and that's equation number 2, the two equations for Timoshenko beam theory. When you just differentiate this, you get d2y over dx2 minus d theta over dx equal to v prime, derivative of v with respect to x, shear force, divided by kGa. And you can indeed see that d2y by dx2 is not equal to d theta by dx. You have this extra term. If the shear force is varying, then you cannot get d theta by dx through the second derivative of center line, because theta is an independent variable here. Okay. So, yeah, I mean, eventually you have these two equations which you have to solve to get the deflection using Timoshenko beam theory. Yeah. No, this is also not true. See, we could work with this formula for curvature only for EBT, even the nonlinear formula. Because, see, this is eventually the curvature of the center line. This is independent of how two cross sections here will pull or push. The pulling or pushing of cross section here will not come through what is the center line doing here. It has to come through what's happening to the orientation of the cross section. Are they changing along the X, or they're not changing? Only then they will either push or pull each other on two sides of the center line. Yeah, that's a very good question. Yeah.
Maybe we got two questions.
Yeah, sure.
So one is the first is what is the relation between G, the moduline G, A, E, and I?
Yes.
I mean, is there a relation between them?
A is a geometric property. A is the cross-section area. G is shear modulus of the material of which the rod or the beam is made.
So proportional to E.
Yeah, I mean, depends on the Poisson's ratio, for example, G is equal to E over 2 times 1 plus nu. I is the second moment of area, which is again a geometric property.
Square, the D4?
A is the area, so it is D square. I goes as D4. I goes as D4, yeah, that's a very good question, and everyone should know that I, where is I? Yeah, here. That's actually second moment of area, no? It's Y squared dA, for example. So it scales as D to the power 4, whereas the area, cross-sectional area, that scales as D square. Yeah.
Can we see Euler-Bernouli as G goes to infinity? No, or GA goes to infinity, then you recover.
Yes, because once that happens, then the shear strain that generates will be very small, right?
Yes.
Because that shear strain, you can see here, gamma C, that's the shear strain, is the shear stress by G. And if G becomes infinity, then gamma C is definitely becoming close to 0. And then dy by dx is same as theta. And then it's going to work.
And when E goes to 0,
The G.
D.
D.
D goes to 0.
Oh, I was not saying about D. I was saying about G, shear modulus G.
Yes, no, because for plates, but also rods, sometimes you want to take the limit of very thin.
Yes, yes, yes.
And to see this very thin limit, which one the models you should take, and they.
Yeah. Okay. I'll also address that problem in maybe in my next example. What happens as a rod becomes really thin? Yeah. So the question basically is which one to use? Do we use Euler-Bernoulli beam theory or Timoshenko beam theory? Definitely Timoshenko beam theory is more accurate, but then it's a bit more complex. You have to deal with two equations. So when do we, is there some realm in which Euler-Bernoulli beam theory will give a very nice result or as accurate as Timoshenko beam theory? So maybe I should address that. I have some time left. I can do that. Okay. Yes. Yes.
Is it?
Oh, it's a purely sectional property, purely cross-sectional property. In the realm of linear elasticity, it's purely cross-sectional. It's a purely geometric property. But for non-linear elasticity, it could be that it also depends on the material property. But the linear elasticity solution for the correction factor is purely geometric property. Yes. Yes.
Last equation that you have essentially is moment balance for some infinitesimal sector. But there's also the normal force balance that you still have to.
You mean the shear force balance?
The axial force.
Yeah, so we are not worried about the axial force in these two theories. Even in the Timoshenko beam model, yes.
The question was, does it appear in the higher order?
Of course, in the rod theory that we'll talk about, maybe tomorrow, we'll have that equation also. Yes. Right. So the next question, as one of us already figured out, is a good question, is EBT versus TBT. EBT means Euler-Bernoulli theory, and this is Timoshenko beam theory. So which one do we use? So I'm going to address that through a very simple example of a cantilever and subjected to this transverse load P. So the equations of Timoshenko beam theory is EI, something that is already derived there, d theta over dx equal to m of x, which in this case is p times L minus x, right? This is something also derived in the board. And then dy by dx is, let's say this minus theta is shear force V of x over correction factor KGA. So just as we found out the moment profile, how the moment is varying along the beam, we have to also find out how does shear force vary along the beam. Now, in the same way, just as you did for the bending moment, you cut a section here at a distance x from the built-in end and draw its free body diagram. And this is a negative normal cross-section. So shear force is going to go down, V of x, and bending moment is going to go clockwise, M of x. And on this end, you have your P only. And when you do simple force balance, you can see that negative V of x plus P is equal to 0, or V of x is equal to P. What this tells us is that the shear force is constant in this case. Okay, so P of x can be replaced by simply this parameter P by KGA. So you have these two equations to solve for, and subject to the boundary conditions, of course, here. First is y of 0 is equal to 0, because this is a built-in end, it cannot move up and down. Can you guess what's going to be the next boundary condition? dy by dx equal to 0? Yeah, so if you say dy by dx at 0 equal to 0, that is not right. you have to look at the physics. The cross-section is built in, so cross-section is not allowed to rotate here. And that's coming through theta. dy by dx is the center line tangent. That is not fixed here. Because of shear, it need not be aligned with the cross-section normal. Okay, so this is a wrong boundary condition. The true boundary condition in this case is theta of 0 equal to 0. So once you plug them in, you solve these two differential equations. It's a first order system of first order differential equation, linear differential equation. You can actually integrate this because the right-hand side is fully known. You integrate this, you get a constant. Integrate this, get another constant. So two integrating constants, two boundary conditions. You plug them, you get your deflection formula. Okay? So that turns out to be y of x equal to p over ei into L x square over 6 minus x cube over 6 plus px over kGA. That's the deflection formula. And if you look at what is the tip deflection, y tip, you just plug in x equal to L here, you get L cubed by 6 minus L cubed by 6. Okay, am I doing something wrong? Yeah, this is 2. L cubed by 2 minus L cubed by 6. That's going to become, I think, L cubed by 3. Yes. L cubed by 2 minus L cubed by 6 is L cubed by 3. So y tip is going to be PL cube over 3EI plus PL over KGA. That's the tip deflection using Timoshenko beam theory. You can say in the subscript TBT. And this is the extra deflection that you get because of the shear. Extra deflection. Yeah. Yeah. So at this end, because it is clamped, so it cannot move up and down. So y of 0 is equal to 0. But the second one, if you say that dy by dx is 0, that is not correct. Because what does physics say? Physics says the whole cross-section is built in. Cross-section cannot rotate here. And that's coming through theta. Why is it that dy by dx is not equal to 0? Because they are no more independent of, they are independent of each other, right? If there is shear, then there can be angle between the normal and dy by dx, which is there in this case for TBT. Yeah. So that's the deflection in the Timoshenko beam theory, and that's the extra deflection that you are getting. If you do the same thing for Euler-Bernoulli beam theory, then YT, EBT is simply the first term, PL cubed by 3EI. Then one can ask how much is the error. So the error, let's say relative error, that's going to be YT, let's say TBT minus YT EBT divided by, we would say that Timoshenko beam model is more accurate. Let's divide by Timoshenko beam model deflection. So this is going to be PL over KGA divided by this deflection, the whole thing, which is PL over KGA plus PL cube over 3EI. If I divide by this on both numerator and denominator, then the error is going to be 1 over 1 plus this over this. P is going to cancel, L is also going to cancel, and it's going to become L square. So I'm just going to use my notes. K, G, A, L square divided by 3 E, I. That's the error. And we want that this error should be small, no? If EBT should work, then this error should be small, which means this number should be much, much larger than 1, right? Then only denominator will be like, let's say 10 or 100, and then the error would be 1%. If this is 100, then the error would be 1%. 1 by 100 is 101, 1% error. So we want this to be much, much larger than 1. K, G, A, L square over 3 EI. This should be much, much larger than 1. Now, what we can do here is keep the material properties on one side and geometric property on the other side. So this is going to become G over E. Let me see how I've done here. So okay, so I also write the I, supposing it's a rectangular cross section, then I is actually 1 over 12 BH cube, where B is the width, H is the height, 1 over 12 BH cube, and correction factor K is 2 by 3, and area is simply B into H. This thing you can write as BH into H square by 12, and BH is the area, so this is A into some radius of gyration square. You know, that's how we deal with second moment of area. You know, area times radius of gyration square. The equivalent radius for which you get the same second moment of area. And then RG becomes your cross-sectional dimension. So once you put all that in there, you're going to get K, G, L square divided by 3 E RG square, much, much greater than 1, or L by RG whole square, slenderness ratio, L by RG, much, much greater than 3E over KG, which turns out to be 6 times 1 plus nu over K. So L by RG should be then much, much greater than the square root of this. And if material, if it is, let's say, incompressible, nu is of the order of 0.5, 1.5 into 6 is 9, K is of the order of 1, so it's close to 10. So L by RG would be much, much greater than the square root of 10. The square root of 10 is, I think, about 3.162. You can see that if it is much, much greater than 3, you know, something like, let's say 15, 20, of course, you can go further beyond, then Euler-Bernoulli theory will give a very good result. But if it is close to 3, then there will be error if you use Euler-Bernoulli beam theory. Okay? So I think I'm going to stop here. And if I have some time, I can take questions. Yeah. Yes.
In the solution.
Even here?
Yeah, so you get a non-zero dy by dx because of the first term. I would have expected only it will show because of the second term. Because here, right?
You will, when you take the differentiation and evaluate at x equal to 0,
Yeah.
you get 0?
Oh, x equal to 0, right?
Yeah, only at x equal to 0. Yeah. Yeah.
Confused by this last result because you anyway would assume that this L over RG is, large, no matter which beam theory you would use. So this would suggest that values Timoshenko anyway, because the difference seems to be when you are kind of out of the beam theory limit anyway.
Well, much, much large means how much large? If L by RG is 100, or let's say even 25, okay, you can use Euler-Bernoulli beam theory. But if it is of the order of 10, then this says that it will give you some error, right? L by RG, this is 3. 3 and 10 are close to each other. If it is 10, the Timoshenko beam theory will give you better result. Yeah. And also it depends on your Poisson's ratio. And here we assume that it's an isotropic material. What if the material is anisotropic? Then the constants will come in a different way. And what you will have is this constant, which is the shear stiffness of the beam and the bending stiffness of the beam. These two do not have the same formula for more exotic materials. If it is anisotropic or if it has some microstructure, then they do not have the simple formula. And then the material properties could be such that what you get on the right-hand side is not really 3, it is something else. Yeah. Yes.
If you're getting an effective 1D theory, how does anisotropy play a role? I mean,
Yeah, right. See the anisotropy, if you look at the equations, where is it showing up? This EI and this KGA. So EI is the bending stiffness and KGA is the shear stiffness of the beam. This will have different formula if it's an anisotropic beam or if it is an exotic beam having some microstructure. Then these two will come through some homogenization.
You finally want some effective value because it's a one-dimensional.
Yes.
Another question, if you want to include dynamics into this, we just add a y.
Yeah, you'll have a right-hand side, yes. Yeah, that's a good question. So just to demonstrate, we took a very simple problem of cantilever. If we had a problem with different boundary condition, of course, you will not have the same result. But in the end, it will be something like this, L by RG, much, much greater than some different number. But it turns out, and also from different examples that people have worked out, and from numerics, that if L by RG indeed is much, much large, then for all loading conditions, EBT will be you can trust EBT. Yeah. Yeah, you have. Oh, okay, yeah. Yes, from designer perspective, yes, because it is giving you higher deflection, so you should design using TBT. Is that what you're saying? It is anyway more accurate. So it also depends on a designer. At the end of the design, they always have some factor of safety. So even if they work with Euler-Bernoulli beam theory, they will say, let us have some factor of safety to account for the modeling error. Yeah. I mean, it depends on the designer. Does he want to have a more accurate, but at the same time more complex design process, or a simpler design process. It depends on him. If at the end of it, he is trying to have some, see, if you really ask this question, the only solution is the one which gives you the most accurate result, right? Then it's TBT. But then it's also about the simplicity of the design process. Sometimes it's also the case, because you always have some factor of safety in the end to work with. Yeah.
More questions? Let's thank Ajeet.
Thank you, sir.
We'll just wait here for 5 minutes because the ICTS director will be giving a brief intro about ICTS. We'll just check.